So region between the graphs of y equals 1 and y equals the sine of x. So that's all this stuff here. I'm going to unshade this in a second, like that. But that's really what it's talking about. That region is getting spun around the axis. All right. The biggest question I had when I was a student is how do you know? How do you know to use this method versus washer method versus shell method? Well, I was about to tell you when you know to use washer method. The shell method, which we'll get to next time, that's a little bit more gray area because that one is dependent on your ability to use the shell method. Okay, so it's like you start using it and it doesn't work. That means that you shouldn't be using the shell method. All right, but going into a problem, you can't always tell. But in this kind of situation, you can tell. It's a washer method if your bounded area is not adjacent to the axis. All right, so washer, bounded area, not adjacent to the axis. I would say axis, but just to be very clear, axis of revolution. The axis that you're revolving around, just so you don't think I'm talking specifically always about the x-axis or y-axis. The last problem we did, the axis of revolution was the line y equals 6, so it can change. All right, so how do we handle this? We're going to do two disk methods and then subtract. So we're going to do a disk for the outer function and then from that we'll subtract a disk for the inner function. Outer and inner is all relative to the axis of revolution. So start with the one that's further away from the axis. Then go to the one that's closer. So I need basically a pi r squared minus a pi r squared. You do it within the same integral, but I really want to emphasize that all this is you doing the disk method twice. Which, you know, my foreshadowing I think was appropriate. Disk method is really important in order for you to understand the next topic, which is more disk method. It's a pretty solidly appropriate, I think. So we'll look at the outer function. Just the line y equals 1, that's nice. I'm going to create my arbitrary rectangle going from the axis out to the function. That arbitrary rectangle is going to have a thickness dx. The function itself is y equals 1, so I'm just going to put the number 1 in there. All right, that's the outer function, y equals 1. Then I'm going to do another arbitrary rectangle going up to the innermost function, also a dx. This time I'm looking at the red function, which is y equals the sine of x. So just the y value, sine of x is going in. I need some bounds. One is easy enough, that's 0. The other, I need to, no, I don't need to figure it out. I was going to say I need to figure it out by finding the intersection, but we don't because they gave it to us. Pi over 2. All right, so these two integrals, when subtracted, will give you the area, the bounded area, the correct bounded area, revolved around the axis. So just that little sliver of area, this little triangular wedge here, just this part is getting spun around. All right, and so I want to take the whole thing, create a cylinder out of that, and just carve out this area here between the curve and the x-axis. I want to carve out that area revolved so that it's basically boring out the guts. It's kind of like you take a loaf of bread and you're pulling out the guts of the loaf of bread. And I'm not talking about like Wonder Bread, because that's already sliced. Why would you rip out the, that doesn't make any sense. I'm talking about like a nice loaf of French bread, you know, something along those lines. Anyway, another way of writing this, because the bounds of integration are the same, I can write it as one integral, pi times 1 squared minus pi times sine of x squared dx. Also, because there's a common pi, I could write it going from 0 to pi over 2 with a pi in front, 1 squared minus sine squared. So if you're the kind of person that likes shortcut rules, which is most people, it would be pi on the interval of a to b, r squared minus r squared dx. So a pi r squared, a pi r squared. But if you pull out the pi's, it's really r squared, r squared. You go capital for one, lowercase for the other to distinguish between the two radii. You'll have one that's bigger than the other. The one that's further away comes first, the one that's closer comes second. So you could go this route, but I like doing it this way because one, it's building off of my understanding of the disk method, and two, I'm looking at something that's clearly the area of a circle formula. Right? It's popping out at me. I'm looking at area of a circle, area of a circle. By applying thickness to that, it's making it into a three-dimensional figure. Here, I look at this and I see it's just another formula that I have to memorize. Right? It just means more to me. But you may completely disagree, and that's your right, and I allow you to have that right. You can go either way. You might find another way that you like better than the way I teach this stuff, but considering that I didn't understand any of this crap when I first saw it, I had to come up with ways to actually make it make sense to me. And so I like to think that I came up with something reasonable. Question? Yeah, it would be with respect to y. Another variation of this would be the same stuff with a dy, but you would have your arbitrary rectangles horizontal. All right. And just understand something. For disk method, for anything involving volumes, you can't arbitrarily change your perspective like we could with areas. Like I said, I could find the area using integration with respect to x, but it's so much easier to do it with respect to y. That's fine for area. For volumes, if I try creating a horizontal rectangle here, if I were to spin that around the y-axis, I'd get a completely different figure, which would have a completely different area. All right, so you don't have as much choice in this regard as you would in the case of areas. All right, so more stars for you. Stars, stars, and then we'll get to shells next time. But you definitely want to digest this a little bit first. It takes a little bit. So that's page 19.